All right, so this week we're doing the Induction Lab. So I'll have 2 videos for this one. So this will be the introduction part, and then I'll show you also in the second video the experimental setup and how you're actually going to do this lab. But the induction, what this says is what? So turns out that if I had, say, a loop of wire, so here's my loop of wire, and then I move a magnet near the loop of wire, so let's say this is the north side and this is the south side, we can actually induce currents inside of this wire. So a nice way to kind of show that is here. So here what I have is there's a loop of wire, here's my magnet, here's a light bulb. So initially, if the magnet is sitting still, I have no light going on inside of the light bulb. But if I start to move, then the magnet here, there's a massive delay. Let's see. There we go. So as I move this guy, I can actually create then a current flowing through the wire, which actually will cause the light bulb then to light up. Right? Now, the reason that this happens is basically by moving the magnets, you can actually then generate a power supply, or basically a potential difference inside of the wire, which then causes the current to move, which then causes the light bulb to shine up. Okay, so this particular type of potential difference is generated in what's known as a induced EMF. So this is induction. So basically what happens then is we can induce, so I knew how to spell, there we go. So we can induce a current by inducing an EMF inside of the wire. So this type of EMF, or this type of induced EMF, is then equal to minus the time rate of change of what's known as the magnetic flux. So basically, and the magnetic flux is the same thing as the electric flux. So here, this is then in general the integral of the magnetic field dotted then by the differential area. So if I wrote this out, this would be equal to minus ddt integral of b dot dA. So basically what happens then is, if we think about the magnetic field lines on the magnets, what's happening is I have magnetic field lines come out from the north side, go back into the south side, come out from the north side and go back into the south side, right? So this is my magnetic field. So what's really happening here is, if I look at a portion of my magnetic field lines, I have my magnetic field points in this direction. Let me draw a little bit more magnetic field lines. Let's draw another one that kind of does this, wraps around, and then draw another one over this way that wraps back around. So initially, when this magnet is sitting still, I have simply, say, 2 magnetic field lines which are penetrating through this area. But as I start to move my magnet downward, say I'm moving it in this direction with a velocity v, what happens then is at a later time, more of these magnetic field lines then are going to burst through this area, which means that now the flux has increased, causing more magnetic field lines then to pass through this particular area, which then causes the flux to be changing. So here, even though the magnetic field itself is actually time independent, because this thing is actually stationary based off the fact that magnetic field is based only on the strength of the bar magnet itself. But what's really happening is that the number of field lines which are passing through this area is changing with time, which then causes it to induce then this EMF. So the induced EMF then is equal to negative of the time rate of change then of the magnetic flux. So what's important here is that the flux is changing, not necessarily the magnetic field. Now, this can happen one of 3 ways. So the ways that this can actually happen. So number 1 is the magnetic field itself can be time dependent. So in this case, I could put this loop into a magnetic field like electromagnets and then turn up the size of the current. So the magnetic field itself is changing as a function of time, which then causes it to induce an EMF inside of this wire. That's the first way. The second way is we could change the area as a function of time. So here the area is actually time dependent. So in this case, I can actually change the size of the loop. So I could grab the loop and pull it so it becomes bigger. I could squash the loop. I could change its area. Or the third way is, remember that the integral of b dot dA is the same thing as the integral of b times dA times cosine of the angle between the two, which means the other way we could change this is have a time-dependent angle, which means that I could actually rotate the wire or the loop inside of this external magnetic field. So here, my angle could actually be time dependence. Okay. So these are the three ways, or any combination of these, that we can actually then generate an EMF on the inside. So again, what's important is that not necessarily the magnetic field itself is changing, but that the number of field lines or the flux, which then passes through this particular area based off of the coil, then is changing with time. Okay, so this is what's known as induction, or this thing is actually what's known as Faraday's law. So this is what Faraday's law says. Now, this negative sign here now has its own interpretation. This is what's known as Lenz's law. So let's talk about Lenz's law. So Lenz's law is all the interpretation of that negative sign. So what Lenz's law says is that the direction of the induced current is such that it is to oppose the changing magnetic field. All right, so what does that mean? So basically what that means is what? What really happens is the coil itself creates its own magnetic field, where that magnetic field is induced in such a way to oppose the changing external magnetic field or external magnetic flux. So what does that mean? So what that means is, let's say go back to here, let's say this is my north side, south side, so that initially my magnetic field is pointing downward. So this is my B field. And let's say that my magnet is moving inward. Okay, so it's moving in with a velocity v. So basically what's happening is what? As this magnet is moving then towards the wire, the magnetic field inside of the wire then is increasing, which means that the magnetic flux is increasing, which means that this external magnetic field then is increasing. Now, what Lenz's law says is that this guy, the wire then, is going to induce its own magnetic field called an induced magnetic field. So this thing is called an induced magnetic field, where that magnetic field then, which is induced in such a way to oppose the change. So here what's happening again is that the flux is increasing inside of this wire, which means that this magnetic field, which is pointing downward, is getting bigger, which means that the wire then induces its own magnetic field in the opposite direction as this this external magnetic field, to keep this thing relatively the same size. So what the wire wants to do is maintain status quo and maintain that the total magnetic field is equal to the original magnetic field when this magnet was stationary. So to do that, it wants to induce a magnetic field which is opposite to the direction of the changing magnetic field, to then cause it be the sum of the two magnetic fields equal to the original magnetic field. Now, what this does is this guy is being induced because then a current has to flow inside of the wire, and this is going to flow in such a way to increase or induce this magnetic field to be pointing in this opposite direction. Now, right-hand rule number 3, which is basically the same idea as what the the magnetic moments, says that the way to induce this magnetic field is we have to curl our fingers around in the direction of the current, and then our thumb points in the direction of the external magnetic field. So here, since I want my thumb to point upward, my fingers have to rotate around in this direction, which means if I was looking down on this wire, my current would have to be flowing then in the counterclockwise direction. So here, I'd have to have current then flowing in this direction. So this is going to be my induced current to induce this magnetic field, which is then actually happening because I'm inducing an EMF, which is causing the charges to move in this direction to induce this current, which then induces this magnetic field. We'll have to use this term induce a lot. Now, what happens if I do the opposite? So now here is my coil, here is my bar magnet. So here's my bar magnet, north side, south side. So the bar magnet still has magnetic field pointing downward. So this is still B, but instead I'm going to pull it upward with a velocity of V. What's going to happen in this case? Well, now, pardon me, the external magnetic field still points downward, but what's happening now is as I'm pulling the magnet upward, what that's going to do is it's going to cause this magnetic field to decrease, or more appropriately, it's going to cause the flux to decrease. Now, the wire doesn't want the flux to decrease, it wants the flux to remain the same. So what this thing is going to do then is it's going to create a magnetic field in the same direction as the external magnetic field. So my induced magnetic field then is going to be in the same direction as the external magnetic field, because the external magnetic field is decreasing. So in this case, I need my thumb to point downward, so I have to rotate my fingers in the direction of the induced current, which means in this case, my induced current then is going to go in the clockwise direction when looking down on it. Okay. So what'll happen is, as I'm moving it down, the current's going to flow in the counterclockwise direction. When I move it up, the current's then going to flow in the opposite direction, then in the clockwise direction. So this is Lenz's law. So again, Lenz's law is the interpretation of the negative sign on Faraday's law, which says that the direction that the EMF is being induced is opposite to the direction of the changing external magnetic field or external flux. So it always wants to try to keep the flux constant or magnetic field constant by inducing its own magnetic field to counteract the changing external magnetic field. Now, so here we have to be a little bit careful. We have to pay attention to the direction of the magnetic field and what is that magnetic field doing? Is it increasing or decreasing? Because that's going to change the results of what actually happens here. So this is what we're doing in this lab. So in this lab, we are going to be playing with and making predictions based off of Lenz's law primarily on what direction is the current going to be moving based off of what the external magnetic field is doing. So in these cases, especially for part C, you're gonna be taking a bar magnet, moving it inside of a coil. And here we're gonna play around with the different directions of the external magnetic field. So one part, you're gonna have the north side going in, north side going out. And the next part, you're gonna have the south side going in and then the south side going out. So here, again, we have to pay attention to what's actually happening. So what direction is the external magnetic field pointing and what is it doing? So is it increasing, which is what it's doing here? So what's happening here then is my external magnetic field is increasing, while here my external magnetic field is decreasing, or more appropriately, my flux here is increasing and my flux here is decreasing. Because again, technically the magnetic field is actually constant. So again, in this case, since my external magnetic field is increasing, then I have to induce my external or my induce an internal or induced magnetic field in the opposite direction to counteract this change. And in this case, I have to induce the magnetic field in the same direction to again counteract this change. With the south, it's going to basically be the same thing, except the fields are going to point in opposite directions because now my magnetic field will be pointing in this direction upward instead of downward. So we'll have to pay attention to those. But again, in this lab, that's all we're going to be doing. So we're going to be using Lenz's law to make predictions on what direction is the current going to be moving throughout the coil based off of the direction of the deflection of the galvanometer meter. And I'll talk about that in the next video. So you'll be able to watch that and see what happens there. So, but again, this is Faraday's law. So Faraday's law simply says that anytime I have an external flux increasing or decreasing or changing in any way with some sort of closed loop, that closed loop then will have currents moving through it because a voltage is induced inside of this because it wants to create its own magnetic field, which is going to counteract the way that the external magnetic field is changing. So this is called Faraday's law. So Faraday's law is used for a lot of different things. We'll talk about those in class, but this is what we're going to be playing with in this lab.